So hello from Virginia. So I'm going to talk about our paper on incremental perception. So this is a very quick summary of the paper. So our goal is to address perception inefficiency in self-driving paradigm. So the key observation here is 3D perception has extensive research, but if you look at the research, it's sort of optimized independent of downstream tasks. So by downstream tasks, I mean control, prediction, and planning. So our proposal here is we should make downstream tasks guide the perception to tell perception where to look at, so that perception spend resources on the most relevant details of the scene. So a little bit background about autonomous vehicle. As you can see on this picture, you have various sensors mounted on the vehicle. At the runtime, these sensor data will be fed into perception module. So this is a, let me turn on my laser pointer. So this is a software module, and the perception will give you object detection results, like where are the surrounding objects, what are the environment, where are the roads, where are the sidewalk. So the outcome of perception will be fed to downstream tasks, localization, planning, prediction, which will be further fed to the control module, which will generate commands to the actuator of the vehicle. So a little bit about 3D vision. So we are talking about the data generated by LiDAR. So the data is in the form of point clouds. This is an example of 3D vision pipeline. You don't have to read in the detail. Basically, the idea is the point cloud will be ingested and it will fall into multiple stages. For example, multiple levels of 3D sparse convolution. The convolution layers will summarize the 3D points at different levels of granularities. It will extract different features. Then eventually, this perception algorithm will generate 3D bounding boxes as well as the classification labels for that for each object. So our observation on today's 3D vision research, number one is it's very expensive. So we profile it even on a modern GPU, a desktop, a discrete GPU. Every frame, every point cloud frame, it's going to take 100 milliseconds. And you are looking at like 10 frames per second. In the real world deployment, that time is going to be even longer. The reason is that on real vehicle, you have energy constraint, thermal constraint, and you have multiple LiDARs. You are looking at 4 to 6 LiDARs these days. And all of the LiDARs are generating this 3D point clouds continuously. And the GPU is not only used by perception, it's also used by other tasks. So the perception is the bottleneck in today's autonomous driving software stack. Another observation is the usableness of the outcome of the perception is solely measured as accuracy, right? So look at all these vision papers, right? So the way they evaluate the efficacy of the algorithm is they have, for example, this IOU. So basically, they try to say, oh, you predict there is a bounding box, right? So how much overlap this bounding box has with the ground truth, and whether you predict that labels correctly. And they use this, for example, median average precision as the measurement for the outcome usefulness, right? Of course, there is efficiency, but the outcome usefulness is primarily measured as accuracy. Now, our observation we identify two missed opportunities. Number one, the accuracy for many times fails to capture the relevance of the outcome to downstream tasks. What does it mean? So you have object detection results, for example, how useful this is not only depend on the errors in that result, it also depends on, for example, the timings. So will you rather have inexact yet timely detection results, or you would prefer exact yet very slow detection results? So we will show this answer is not straightforward. I will show some data later. And there are different types of errors. Will you rather have low spatial errors, which means very accurate bounding box, or you would rather have low classification errors. So the second missed opportunity is the vision algorithm these days, right? So they sort of lack target attention. Think about how humans drive. We drive, right? We pay attention to the road, but we sort of steer our attention to the most relevant objects on the road. For example, there are vehicles in front of me, right? I pay more attention subconsciously. I pay less attention to other objects, for example, on the sidewalk or vehicles behind me. So that is missing in today's 3D vision algorithm, and it's a waste of resources because it tries to see everything clearly in the driving scene. So some data here just to motivate what I said. In this figure, we show how as you sample more data, more points in a point cloud, you will have better accuracy for the object detection. Right? That's natural, right? So this is for one given frame, right? So more percentage of point cloud data, higher accuracy. Now, on the other hand, the more point data you have to process, the longer time it has to take. Then even after you have the detection results, the time left for you to take action is much less, right? Then that is reflected by the safe distance for the vehicle to stop is minimized, is reduced, which means in order for you to safely stop, now the vehicle, the obstacle has to be a certain distance away, right? If the obstacle is closer by that distance, then you will have a collision. So the takeaway message here is, yes, doing more in perception gives you better detection results. However, at a longer delay, right? The time to decision is longer, which may not always be good for your driving safety. So to fix this problem, our principle is to no longer focus on the perception itself, but co-design perception and downstream driving tasks, notably planning and prediction. So we showed this picture before. Our proposal is to add a feedback path from the downstream tasks back to the perception. So let the downstream tasks tell the perception which parts are more important, by which objects are more relevant that you should pay more attention to. So our proposal is called incremental perception. To be more specific, each 3D frame is processed in multiple iterations. So there is an initial iteration. The goal is to generate very quick results. The results can be inexact. For instance, the rough 3D bounding boxes, there could be labels, or the labels could have misclassification errors. Then the inexact results will be given to downstream tasks like planning and prediction. And downstream tasks could do two things. Number one, if the inexact result is already having high confidence, then planning and prediction can take action based on the inexact outcome. So as a result, your vehicle can react to emergent events with lower delays. On the other hand, if there are some interesting events, but the perception outcome does not have high enough confidence, then at least the downstream tasks can send feedback to perception, say, oh, that object has high significance to how I plan the future driving, right? So I would need further iterations, right? Further processing of the 3D point cloud, so that I can see better, I can make better decisions. So with incremental perception, many key optimizations can be enabled. Number one is early exit. I just mentioned that, right? So because now previously you process the entire 3D point cloud in one shot. Now you process it in multiple iterations, and you can do early exit. You don't have to, for many frames, you don't have to process that frame in full before you can make any decision. The second is attention. So essentially, the downstream tasks with its own knowledge can steer the perception's attention to the most relevant pixels or details of that driving. I'll give you two use cases. Right? Number one is motion planning could guide perception. So motion planning is happening periodically when the autonomous vehicle is running. So every a few hundred milliseconds. So every update will include the new objects and where the ego vehicle will go, the future trajectory for the ego vehicle. So the trajectory will have different sensitivities to objects around you. I mean, as I mentioned earlier, right? So some objects will sort of intersect with the trajectory, which means there is a vehicle in front of me, or there is a obstacle, some pedestrian sort of jump to the road. Right? So that objects have high significance or sensitivity. Therefore, motion planning can tell the perception module say, oh, those objects are really important. I need their more accurate bounding box coordinates. I need to see their class labels more clearly. Okay, so you can further refine those objects. I mean, on the other hand, if the object is not intersecting with the trajectory, you don't have to pay attention to that. Use case two is the downstream task will do prediction. So this is a well-known notion. It's called the risk estimation. So some software module in this autonomous driving software will continuously estimate how much risk each surrounding object is posing to the ego vehicle. So it depends on many things. The risk depends on many things. The motion patterns of those vehicles, the road condition, right? So the traffic flow, whether the lighting is good or bad. So this example shows that some passenger vehicles, right, following the traffic flow near me and is moving in a regular pattern has low risk. Therefore, your perception may not need very accurate results on that. Maybe somewhat accurate is good enough. On the other hand, there is a lane changing like semi truck, right? So it's big. It's sort of it's changing the lane. Therefore, the risk is high. You can the risk estimation module can give feedback to perception, saying, "Oh, that is really dangerous, right? I need more accurate label. I need the bounding box in a more accurate fashion, right? So to require the refinement. So I will show some a more concrete example. So this is to show what will happen if you have one short perception versus when you have an incremental perception. So in this example, we assume you are driving on the road, and at time 0, which is on x-axis, there is an obstacle suddenly appear. Could be somebody, people, right? Suddenly show up in the middle of the road. So the distance is about 80 meters away, right? That's the initial distance. Now, as this obstacle shows up, so it has been captured by the sensor at that moment, registered by LiDAR. However, the LiDAR data has to be processed. So what you have is the 3D frame is being processed. It will take some time. Okay, by the time the object is detected and the decision has been made, it's already a little bit late, right? Because this is one shot perception, right? It will take long to process one frame. Then there is no much time left for the vehicle to make a brake, right? So you have to brake really hard to avoid colliding with that obstacle. Then hopefully you can stop. But the experience is really bad, okay? Because there is jerk, right? There is a sudden deceleration. On the other hand, with our incremental perception proposal, so the same idea, the obstacle will show up at time 0, then it's captured by LiDAR. So we will generate inexact results with lower delay. The perception will run the first iteration, it will detect that object. Although the bounding box of the object may not be very accurate, although the label for the object may not be very accurate, at least, right, there is some confidence showing, hey, something showing up, maybe it's good time to sort of gracefully decelerate to avoid, to mitigate the risk. So we decelerate, then the planning module will require further refinement of the point cloud. So after a certain amount of time, the object is refined. Now the planning module can see that object better, or it's indeed a human, and I can sort of better estimate its moving pattern. So I do replanning with more accurate deceleration. So I can sort of gracefully decelerate throughout, right? The end result is the vehicle slowdown is smoother, it's less vehicle jerk, and the passenger comfort has been improved.
Felix, you should wrap up.
Okay, so let me skip all these challenges and let me recap. So we talk about incremental perception on real-time 3D data. So the problem is the current pipeline, autonomous vehicle pipeline, is slow and redundant. The perception has been optimized in an isolated fashion, and the incremental perception let the downstream task guide the perception. The benefit is now we can generate driving decision in a more timely fashion, and we identify open challenges on vision, control, and operating system. Thank you.